Okay. Okay, good morning, everyone. We continue today this discussion of beyond the standard model physics. Let me briefly summarize the last part of the previous lecture. So what we've shown in the previous lecture is that in gravity there is an limiting length beyond which you cannot probe physics while staying in GR. Moreover, so there is this Planck length, so approximately 10 to the minus 33 centimeters. And moreover, you can probe actually physics at high energies. And because what happens is that you have let's say you have a box of size L, okay, a pixel. So you are trying to resolve physics at that distance. So to resolve physics at that distance, you need energy which is inverse of that, at least, okay? So you need energy which is at least inverse of that distance. So what you are doing is basically you are creating a tiny microscope, a pixel, that can resolve physics at that scale. So you have to pump energy which is inverse of that size. Eventually what happens is that if you try to continue squeezing this distance L down to a very short distances, eventually you cross the boundary when the whole system here will appear inside of its Schwarzschild radius, okay? So your pixel will collapse into a black hole. After that, if you continue pumping, so this will happen precisely at the Planck length, okay? In GR with just one particle, let's say, okay? It turns out that if you have many particle species, this changes the scale beyond which you can resolve distances. But at the moment, let's stay in GR with just one probe particle, okay? So then, so what will happen is that eventually, so you will reach this Planck length, and you have a pixel, okay, of the Planck size, okay? After that, if you try to resolve shorter distances, you have to pump more energy into this pixel. At this point, when the pixel has energy m Planck, right? At this point, the energy of the pixel is of order m Planck, and the size is inverse Planck length, which means that the Schwarzschild radius, the gravitational radius of this pixel, Rg, is the same, is also the same as the Planck length. In other words, this is the scale at which the gravitational radius and the actual size of a pixel, they cross, okay? So at larger distances, you can use, so at larger distances, the gravitational radius of a pixel is inside of its size, and so therefore, this object is not a black hole. At this point, they cross, and after this, if you try to continue to squeeze it and to try to resolve even shorter and shorter distances, you have to pump more energy, which means that it bounces back. So then it starts, instead of probing short distances, now you start probing large distances, because the whole thing becomes a black hole. If you pump more energy, it becomes an even bigger one, okay? And at this point, the gravitational radius starts increasing, okay? So in other words, in gravity, there is an ultimate limit to a length scale resolution. But amazingly enough, the energy resolution, in other words, what is happening at high energies, we know, because what happens at high energies is that, again, everything bounces back and becomes classical. So this was one thing. So in particular, as we said, this is why gravity is a universal regulator, because, for instance, any particle any elementary particle with mass larger than the Planck scale is no longer a particle. It's a black hole. So this tells you that it simply makes no sense in any theory in which in far infrared at large distances you know that you have Einsteinian gravity. It doesn't make sense to talk about elementary particles which are heavier. Elementary, I mean point-like particles, which are heavier than the Planck scale, because they are black holes. So therefore, the gravity is a universal regulator, and it regulates things at least at the Planck scale, okay? Now, So now we come back to the hierarchy problem. So what this has to do with the hierarchy problem? As we said, in the standard model, okay, in the standard model, as you know, we have different parameters, as we said. So we have fermion masses, Yukawa coupling constants, gauge coupling constants, and the Higgs mass. Now the Wick scale is related to the Higgs mass, as you know. Okay, so let me talk about Higgs mass as a parameter. Now, so some of the so we can classify for our purpose here. We can classify the parameters in the standard model or in general by their sensitivity to the size of the black box. Okay, to the size of the cutoff of your theory. Okay. So there are parameters which are less sensitive, and then there are parameters which are more sensitive. So, for instance, the fermion masses, or Yukawa coupling constants. Fermion masses, if you have the, so let's take the size of this black box, okay? Let me call this cutoff of the theory L, okay? In this particular case that we discussed, this was in Planck, right? So let me call this cutoff L, the size of the box, or let me call inverse size, let me call it lambda, okay? So this is our cutoff, okay? So this is a black box, beyond which our theory breaks down. And so the fermion masses, let's say an electron mass, okay? The sensitivity of the electron mass to the cutoff is only logarithmic, okay? So sensitivity of the electron mass to the cutoff is only a log, okay? Now, there is a reason for this. There is a symmetry reason. So as you know, the fermion masses, they violate so-called chiral symmetry, right? Having a mass for the fermion, a Dirac mass in particular for the fermion, implies that you have a transition between the left-handed fermion, left-handed chirality, and the right-handed chirality, okay? So in other words, if you have a massless fermion, chirality is a good number because there is a symmetry under which you can rotate independently left and right. Once you have a mass, this chirality is broken. But because of this, actually the masses of the fermions, they always get renormalized through themselves. Okay? So in other words, in the limit when you take mass to 0, you restore the full chiral symmetry, which is a very good protector. I mean, you discussed this in the standard model, right? The fermion masses, etc. Okay, so I don't have to repeat. Otherwise, if there is a question, please, I mean, as I said, interrupt me anytime. We go back and rediscuss it. So for the fermion masses, we have sensitivity which is logarithmic. Okay. Now, logarithmic sensitivity, first of all, is not very strong. Secondly, you know actually that whenever this log, because there is also a coefficient in front, which depends on the coupling constants, etc. Whenever this whole thing becomes larger than 1, it simply signals that your perturbation theory broke down and you have to do something. You have to go to the next order or resum or whatever, okay? Now, a very important quantity in the standard model, which exhibits a much stronger sensitivity to the size of the black box, is the Higgs mass, okay? So in other words, the mass of the Higgs, mass square, exhibits sensitivity which is lambda square. So it's quadratically sensitive to the size of the box, inverse size of the box, okay? So in other words, the reason for this, as you know, is that, for instance, Higgs, if I consider diagrams, quantum corrections by virtual particles, let's say here I have top quark running in the loop or some other, or W bosons, for instance, running in the loop, okay? These diagrams, these quantum corrections, they are quadratically sensitive to the cutoff. In other words, they are quadratically divergent. If you cut them off at any scale, you say that, okay, beyond that scale I don't integrate because that's the size of my black box, you will get quadratic sensitivity, okay? Now, as I said, in theory, in a hypothetical world without gravity, okay, this problem would not be so well defined. Why? Because you could always say that, oh, this quadratic sensitivity to the cutoff is an artifact of my regularization, of how I regularize these diagrams. at the end of the day, let me do renormalization, some kind of renormalization, and hide infinities into the physical Higgs mass. And okay, there is one mass scale in my problem. Let's ignore QCD for a moment. And it has to be somewhere, so it happens to be there. Okay? But the point is that with gravity, there is no way out. Why? Because with gravity, we know that, first of all, it doesn't even make sense to talk about infinite energies, because particles carrying an infinite energy, they are no longer elementary particles, as we have just shown. They are classical black holes. Okay? It's the same thing if I run, I don't know, if I run a particle in a loop with an infinite energy, with a huge energy, much larger than Planckian. It's the same as running the, whatever, elephant. I don't know how to draw it, but whatever. Okay. Anyway. Now, so normally we don't run elephants in the loops, right? Now, why? Because we could, because of course, always there is a probability that you have a photon, and the photon will decay into a virtual elephant and anti-elephant. They annihilate, right? No, that's true. There is a. The point is that these are classical objects, and they always give you exponentially suppressed contribution into the path integral. And so therefore, the moment you say that I have some physics which beyond certain scale starts producing, instead of elementary particles, I have to take into account big macroscopic objects which become even bigger with the energy. Okay, you know that this should be this kind of thing should be exponentially suppressed and shut off. So in other words, with gravity, this regulator scale and Planck is real. You cannot simply say that, oh, I continue to the infinite momenta in infinite energies. Or even, I mean, without even considering this, you simply know that with gravity, even if you let the Higgs, whatever, or any mass of any elementary particle to renormalize, it cannot go beyond the Planck. Why? Because after that, it becomes, as we said, right? It becomes a classical object. So therefore, the hierarchy problem, the way it is, it only makes sense together with gravity, okay? So in other words, hierarchy problem is not per se about the big number, but it's about ultraviolet sensitivity of this big number. So other numbers are not ultraviolet sensitive. That's why we are not, otherwise you see, sometimes it is presented in the way that, okay, there is this ratio of MW to whatever scale. Let's take M Planck. And so this ratio is approximately 10 to the minus 32. And the hierarchy problem is because this is small. Of course, this is part of the problem, the fact that this is small. But there are plenty of small numbers in nature, or big numbers in nature. For instance, I don't know, let's take a ratio of the size of human to the size of the universe, right? If I take L human to L Hubble, this will be approximately 10 to the minus 26. This is a pretty small number, but we are not worried about this number. We are not saying, oh, there is a hierarchy problem associated with the fact that we are much smaller than the universe. Or we don't say that there is a hierarchy problem associated with the fact that we are much bigger than the atomic size. Now, why? Again, because of UV sensitivity, because we know that these sizes, they are not fundamental, and they are not UV sensitive to each other. So for instance, the moment you understood the atomic size, you know that humans must be much bigger. Why? Because humans, or anybody else, are the solutions of the equations, some equations of motion. They are not our size is not fundamental. Our size is a solution. We just happen to solve some equations of nature. So, and we are solutions under the condition that we have a big baryon number in us. And because we have many baryons, once you understand that the size of the baryon, you understand that humans must be much bigger, because we include a lot of baryons. Okay? So there is nothing fundamental about our size from this point of view. Of course, otherwise it's very interesting maybe how we evolved to this size. That's a different story. But okay, so this is the point, and this is very important, that this problem is about UV sensitivity. So therefore, now let me discuss. So as we said, the most of the physics beyond the standard model is motivated by this problem. Most of the physics beyond the standard model, which has to do with LHC scale, okay, with this scale, which is 10 to the minus 17 centimeters. Why? Because we think that there is a reason for it. Because of this UV insensitivity of the Higgs mass, there is a reason. And Higgs has to come with some new physics, which will make sure that despite the fact that there is this large cutoff, or despite the fact that there is gravity, the mass gets stabilized where it is stabilized. Okay? Now, this is also a great thing about the hierarchy problem, because it predicts that there must be new physics that solves it. Because the moment you say that the hierarchy problem requires a solution, this automatically tells you that there must be some new physics around that scale, and this new physics cannot be decoupled from us. It cannot be very weakly coupled. It has to be coupled reasonably strongly in order to address this issue. Okay? And this is very interesting. So the question is, what is this new physics? So there are different ideas that I want to review. So first, you can have a certain type of symmetry. Okay? So in other words, what may happen is that above TV energies, you can have a new type of symmetry, which makes sure that this quadratic divergence is removed. Okay? And quadratic sensitivity is removed. There are some cancellations because of this symmetry. And this is called supersymmetry. Well, at least the known example is supersymmetry for this. Okay? This is a very interesting symmetry. It's a new type of symmetry between bosons and fermions, so we'll discuss it. So then you can say that Higgs is not elementary, after all. Okay? So in other words, Higgs itself could be, so for instance, right, let me remind you that we have plenty of spin zero states in nature, right? We have spin zero atoms, etc. Okay. Now their mass is not Planck scale, right? The reason, but we are not worried about it. Why? Because these objects are composite; they are not elementary. Okay. So the same will be true about the Higgs. If Higgs is not elementary, starting from the scale around TV, okay. So then. So then this would naturally tell you why Higgs is why mass is not a Planck mass. Okay. So this is about having Higgs being non-elementary. In particular, Technicolor goes along this direction. Okay. The idea of Technicolor. Finally, the point is that what about gravity itself? Okay. We just discussed that gravity is a universal regulator. We just showed that if I have Einsteinian gravity, which gets strong at the Planck mass, at the Planck scale, elementary particles masses cannot go above that scale. So it's a natural regulator. So then we can ask this idea, what about maybe it is gravity itself which regulates the Higgs mass around TV scale, okay? So this would, let's call it strong gravity at TV. So I will try to briefly go through these approaches. And actually, since we already have momentum in gravity, let me start backward, okay? Let me start from the last one, okay? This is not a historic route. These others were much earlier, invented much earlier, these approaches. But anyway. So in other words, let's assume that what is happening is that gravity is getting strong, not at the Planck scale, but at the TV energy. So in other words, at the 10 to the minus 17 centimeters, okay? So in other words, getting strong means that the meaning that I put in this is exactly the same as what happens in Einsteinian gravity. In other words, what happens is that if I have an elementary particle with mass larger than this new scale, TV, this particle becomes a black hole, okay? So there are different ways to parameterize this statement of whatever, strength of gravity. Look, for instance, we can do like this. We can, for instance, I can do in the following way. I can take a point-like source, okay, or localized source of mass m, okay? And then I can form a dimensionless product by taking this mass and multiplying by the gravitational radius, okay? Sorry, let me not write it here, okay? So let me plot it here. It's more convenient. And here, so there are two axes. So this will be the Compton wavelength of the source, okay? So in there you can parameterize how this product of this source times the gravitational radius, or if you wish, the ratio of the gravitational radius of the source to its Compton wavelength depends on the Compton wavelength, okay? So we can take a source with a certain mass and an elementary particle, so think of it as an elementary particle, and then gradually increase the mass, which means that gradually decrease this distance, and see how this ratio changes. And in Einstein's gravity, what happens is that this will stay very small. I don't even know how to, let me take a different color. So in Einstein's gravity, so here is 1, okay? And this 1 will be crossed at the Planck distance, okay? So this will be the Planck distance. And so we'll have something like whatever, something like this, okay? So in Einstein's gravity, this ratio will remain small for a long time, and then it will catch up around the Planck length. It will become order 1. As we said, this simply corresponds to the fact that the particles of mass, Planck mass, they become black holes, okay? So now what we want to do now is we want to say that no, this is not the picture. The picture may be that actually, let me take a different color, that this 1 here is reached not at the Planck length, but actually at the LHC length, 10 to the minus 17 centimeters, okay? And so the picture is like this. I have, for a while, of course, I have Einsteinian gravity, and then some deviation starts, and then we hit here 1. So inevitably, this tells you that there is a new scale in the problem. Let me call it R, at which the strength of gravity starts departing from the Einsteinian strength, okay? So in other words, the picture here is that at very large distances, the gravity is Einsteinian. Once we move at shorter scales, shorter length scales, at some point, at some distance r, gravity starts slowly departing from Einsteinian gravity, okay? Now, it is still weak here. At this scale, it is still weak, but then it catches up very quickly and hits the maximal strength, not at the Planck length, but actually much earlier. So this is the idea, okay? Now, if this is the picture, of course, this will automatically take care of the hierarchy problem, because again, what will happen here is here now is the same thing that was happening here in Einsteinian theory. So masses of elementary particles cannot go beyond this point, beyond this mass scale, okay? All right, so the question is, so in other words, what we want to say is that the fundamental scale of gravity, let me call it m star, okay, is actually not the Planck mass, but it's around TeV, okay? So now the immediate question that whenever you suggest something like this, of course somebody can come and say, oh yeah, of course it's very easy to say that this is what is happening at TeV scale, but then what is responsible for this transition? How can I arrange my theory in such a way that this happens? So in other words, how can I have a theory which at large distances gives me extremely weak Einsteinian gravity, but at TeV energies, gravity becomes stronger than any other force. It takes over, okay? Now, so to understand what you need for this, let me review, so I'm sure most of you knows this, you guys know this, but let me just remind you that you remember that if I have, whenever I have I'm lost in colors now, so whenever I have a messenger, so now let's discuss forces, okay? So we discussed forces in the previous lecture, and we showed that, okay, for instance, we discussed, for instance, the Coulomb force or Newtonian force as a result of an exchange of a mediator, of a messenger, right, particle. And we said there that actually the usual forces which go like inverse, the potentials which go like inverse R, or forces which go like inverse R square, they are result of the exchange by massless states, by massless messengers, okay? So, for instance, photon is massless, and that's why photon gives us the Coulomb force, which goes like 1 over R square, or the potential which goes like 1 over R, okay? So, in other words, the same is true about graviton. So, in other words, if I have a massless mediator, the potential goes as 1 over R. This is the universal thing, right? Now, again, you can understand this from simply one particle, virtual particle exchange, or you can understand this from with the Gauss's law, flux law, whatever. Now, you probably know what happens if I exchange a massive particle instead, okay? How the forces mediated by massive particles behave. Now, forces mediated by massive particles, they behave differently. What happens is that they are screened at large distances. They are so-called Yukawa type forces. Okay? These forces have the name, these are Yukawa type interactions. So in other words, what is happening is that if you have a source, okay, and a probe, right? So let's say I have a source, some source, and I have a probe here somewhere, okay? And then here's the distance, R. And there is a messenger, right, that mediating this force. What happens is that there is a critical distance which is given by the Compton wavelength of the messenger, okay, by inverse mass. Now, if you are staying within this distance, then effectively things look exactly the same as if you had an exchange with a massless guy, okay? So in other words, this potential here, okay, it gives us the following thing. For distances which are much shorter than inverse mass, this potential behaves like 1 over R. Why? Because the exponent, if R is much less than the inverse M, the exponent is simply 1, okay, and I get this, right? However, at larger distances, when distances are larger than the Compton wavelength, the force shuts off exponentially, okay? Well, effectively you get zeros, okay? Now, you know this, right? I assume sort of that you know this, but anyway, I'm repeating it just to be self-sufficient in this discussion. So, but if you don't know this, you have to remember, this is a very important fact, that the force is mediated by massive fields. They are short range. They cannot extend beyond the mass of the field, okay? At large distances, they are shut off. The long-range forces are the ones which are mediated by massless messengers, always. Okay? If you have a force which can act at large distance, which goes like Gauss law, inverse R, you know that you have a massless messenger in the story. Okay? While the massive forces, at short distances can behave like massless, but at large distances they are shut off. Sometimes we call this screening. They are screened. Okay? So this is a simple fact. Now, so let's remember this and then come back to our story, how to make gravity stronger at short distances. Okay? So we want to have gravity which is Einsteinian at large distances, but at short distances we want to make it much stronger. Now, as we were saying, if I have a source and a probe, right, there is a force because we have a messenger, right? The reason why we gravitate because we have a messenger of the gravitational interaction, which we exchange, graviton. Now, the interaction so graviton, as I said, it has spin 2, it's massless. So interaction by by the exchange that is given by the spin 2 particle, as a matter of fact, is always attractive. That's why gravity is always attractive. There is no such thing as anti-gravity. Among the localized sources, gravity is always attractive. So now, then you can say, okay, it should be easy to make gravity stronger at short distances, knowing what we have already explained. How? Let's add more messengers, right? If I have one messenger, this gives me some force, okay? If I have two, the force is stronger. If I have three and so on, the force goes as a sum of exchanges. So effectively, if I have n messengers, the force that I will get will be n times stronger, literally, okay? So to make gravity, so here is a recipe for you how to make gravity strong at short distances. Arrange your theory in such a way that at short distances you have more messengers. Now, of course, at large distances we only want to have one messenger, the normal graviton. So to have this, the other messengers, they have to be massive. That's the end of the story. So if you have massive messengers, at large distances they do not matter, because force mediated by them, as I said, it decouples exponentially, so we are free, okay? We only have one guy. But at short distances they open up, because we go within the radius of their range, and the force becomes much stronger, okay? Now, this tells you that you can play this game now essentially as you want, okay? For instance, let's assume that we have n messengers at short distances, okay? So for instance, let's take the following story. Let's take a tower of messengers. So this is the mass spectrum, masses plotted here, okay? And imagine that you have a zero mass graviton, normal graviton, and then there is a mass gap. There is a first massive graviton at the mass m. Then I add another one. Let's take the interval to be exactly equal, okay? So I add at the mass 2m, then the next one at the 3m, and so on, okay? I have tower of n states, n gravitons. How the force would look like in this kind of picture, okay? Now, again, the rule is very simple. Each massive guy at short distances of its range mediates the full scale 1 over r force. At large distances it decouples, okay? And there is a collective effect. That's all we have to take into account. And it's very easy. Now let's do it, okay? So let's plot in this story, let's do the following thing, okay? Let's plot, a useful quantity would be to make everything, as you know, right, in physics it's always very useful to make everything dimensionless, because at the end of the day we only measure dimensionless numbers, right? So let's make the following thing. Let's evaluate the strength of the force in this new gravity versus the normal Einsteinian gravity or normal Newtonian gravity, okay? So in other words, let's evaluate a quantity which is the actual force divided by the Newton's force, okay? So that would be a dimensionless number, okay? So this quantity would be, that I will plot here, will be V of new gravity, VR, divided by VR of Newton, okay? So we plot it here, and then here is the distance, r, as a function of r, right? Now, what happens? What happens is the following thing, that so we come from infinity, and so if there were no new excitations in the theory, no new messengers in the theory, then of course this would be just 1, right? So here is 1, and this force would be, let me plot it different color. So this would be just 1, this ratio, okay? Okay? But actually now we have tower of messengers, all right? So what happens is that we come here and then we hit the first massive guy. First massive guy opens up, okay? At some distance inverse m, okay? Inverse m. There is a small transitional region. The exponent takes the power, and then you get 1 again. So, okay? So in the theory in which we had 2 messengers, 1 massive opening up at this scale, this would be the story, okay? If we have 3, this will continue. Okay, so again, the next level, we hit next guy, and the force goes like this. With 4, like this, etc. Okay, so eventually, I'm not plotting it very well, but anyway, you get the idea. So the point is that effectively, if you have many messengers opening up at shorter and shorter distances, the force continuously changes. If you look from a large distance, which is much larger than the Compton wavelength of that thing, or you don't resolve masses or whatever, the picture is as if you have changed the force of gravity, okay, almost continuously. Okay? So it's very simple. So basically what you do is that at every given step, you open up new force, and you become stronger and stronger at short scales. Go at the large distances, they decouple. Okay, one by one they decouple. Now, of course, now we can complicate this game a little bit more. Okay, you can say, okay, but now I want to have, at each level I want to have more than one guy. Okay, you can have certain degeneracy, level by level. And of course, then you can play around with this force. So the force can do some interesting scaling with the distance. So now the question is, so what is the theory? Of course, this is great. I mean, we can design it in this way and be happy. So we can put n new gravitons in the theory, and this would do it. N new gravitons, which are massive, would do this trick. So we can make gravity arbitrarily strong at short distances. But the question is whether there is a natural framework from where this kind of situation emerges. Okay? Do I have 5 minutes or something, or what? 5 minutes. Okay. I think we started late. That's why. Yeah. All right. So actually, this kind of situation emerges very naturally from theories of extra dimensions. Okay. And let me illustrate this on a in very simple terms. Okay. Now, suppose we have a theory in which we have more than three space dimensions. Okay, so we have a fifth. So we have normally we have 4 space times, right? 1 time and 3 spaces. Now let's add 1 extra for simplicity. All right. So we have 5-dimensional space time, and so the coordinates are x, a, and a runs through mu, which are usual 4 space-time coordinates, okay, 0, 1, 2, 3, and then 5, okay. I do it in purpose. I don't call it 4th. I call it 5th, just to make sure that it's extra, not to confuse with time. Okay. So we have these coordinates. Now we have this space, okay, and then there are a bunch of particles that could move in this space, and everything is fine. So now suppose we have 2 observers in this space, okay? So let's call them, usually they're called like Alice and Bob. So what is the difference between them is that Alice is a 4-dimensional observer, okay? So in other words, Alice, so this is 5-dimensional space, and Alice, she lives on a slice, okay, of this space, which is localized at some, let's say, x5 equals 0, okay? x5 equals 0 point. Okay, this is Alice. She is here, okay. And so there is another one, Bob, and Bob is a 5-dimensional observer. And so Bob is here. So the thing is, now, so what it means to be a 4-dimensional observer, it means that from the point of view of a physicist, means that you can only measure 4-dimensional quantities. Your detectors, experiment, they measure 4 momenta, things like this. They cannot resolve 5th momentum. They see 5th momentum as some kind of a parameter, but they don't know that it's a momentum. So now suppose in this space you have a particle, a free 5-dimensional particle, massless for simplicity, happily moving in the whole space. Okay? Now, this 5-dimensional particle has certain momentum, 5th momentum, 5 momentum, right? So 5 momentum would be PA, right? So this momentum has a certain direction. Now, but it has a projection which is 4 momentum projection, okay? And it also has a transverse projection which is 5th momentum, right? Pi 5, P5. And so now, Alice is, so what is going on from the point of view of Bob and from the point of view of Alice? Okay? For the point of view of Bob, nothing special is happening. There is just a particle, massless particle, with a dispersion relation of 5-dimensional massless state. And you know very well that this dispersion relation is just the sum over all the momenta equals 0. Okay? Now, of course, this dispersion relation is the same. You cannot measure, depending what kind of observer you are, in which dispersion relation at the end of the day is the same. So Alice also measures the same dispersion relation, except that for her, 4 momenta are special. So what she sees is that there is a quantity which she would call 4 momentum, but then there is a quantity which is, for her, is a constant. Okay? Now, she cannot understand that this is a momentum. She measures this as a constant. In other words, the same particle that from the point of view of Bob is a massless 5-dimensional particle, from the point of view of Alice is a 4-dimensionally massive particle, okay? With the 5th momentum playing the role of the mass. Okay? So she can simply rename this and say that this is a dispersion relation of a massive particle with mass being given by the 5th momentum. Okay? So in other words, we are led to a very important conclusion that from the point of view of 4-dimensional observer, any particle that freely moves in 5 dimensions corresponds to a massive state with mass given by the 5th momentum. Now, but of course, the particle is the same particle in 5 dimensions, can have any direction in the momenta, right? So in other words, this projection of the momentum can continuously change, right? So this can continuously change. And for the same 4 momentum, for instance, we can have different m's. So what Alice sees that actually it's not just one 4-dimensional particle, but it's actually an tower, infinite tower of 4-dimensional particles with all possible masses, right? Because mass is given by the projection of in the 5th direction of the momentum, and that can change continuously. All right. So this is very important because this immediately tells you that from the point of view of a 4-dimensional observer, a very simple massless particle that moves in 5 dimensions represents an infinite tower of massive states. Okay. Now we can do so in this part. So if this 5-dimensional space is not compact, okay, so then this tower is continuum. So essentially, she sees a continuum of states. However, if tower is compact, so if the 5th coordinate is compactified, nothing special changes, except that what will happen is that if we compactify this coordinate, let's say we compactify 5th coordinate on a circle of radius r, okay. So then what will happen is that as you know very well, whenever you have a compact potential, when you have a compact energy or you have a potential well with periodic boundary conditions, what happens with the momentum? The momentum gets quantized, okay? The momentum gets quantized in the units of the inverse size of the potential well, right? So if I have a compact space, obviously this is like an infinite potential well. I cannot go anywhere, it's just my space. And momentum has to be quantized. And so momentum gets quantized, P5 gets quantized in units of the radius, where n can take any value, 0, 1, okay? Which means that from the point of view of Alice, now what happens is that she got a tower of massive excitations with the mass which goes like a quantum of mass, elementary quantum, is the unit of inverse radius of compactification, okay? So there is an infinite tower of states, and each of them has a mass with which is quantized in units of the size of the dimension. So as you see, larger is the dimension, the states are more crowded. Smaller is the dimension, bigger is the mass gap. So you have a 0 mod, and then you have a first excitation, and so on. Okay. The zeroth excitation, what would that correspond to in the 5th dimension? Zeroth excitation? Yeah, the 0th one corresponds to the one which has no projection in the 5th momentum. The one which is moving across along your slice, 4-dimensional slice. So in other words, for Alice, this would be, oh yeah, it's here. So for Alice, a particle which moves strictly in this direction would be zero mode, okay, with zero mass. Okay, so now this tells you that if we have a theory in which we have high-dimensional space and compactified, from the point of view of four-dimensional observer, we get infinite tower of states. In particular, if we have gravity in the theory, of course, then we get infinite tower of gravitons, but their masses will start from inverse R. So in other words, there will be this tower has a name, it's so-called Kaluza-Klein tower, okay? So in other words, there is a zero mode, normal Einsteinian graviton, and then there is a first excitation, and they are equally spaced in five-dimensional theory, okay? Now, if there are more dimensions, the degeneracy at each level is different, but that's not important for this point. So this immediately tells you that we have exactly reproduced the situation that we were talking about. In this theory, what will happen is that at short distances, gravity will become stronger and stronger, okay? Shorter you go, you have more messengers that mediate force, and eventually gravity becomes stronger and stronger, okay? So in other words, extra dimensions are the way to make gravity very quickly become the dominant force, okay? And catch up with everybody else. Okay, I think we should stop here, right? I think I'm out of time. So, any questions or whatever? There is a discussion session, right? It's amazing. 45 minutes are too short, right? For the lecture.
Yeah, 45 minutes.
So you guys there teach like. So normally it's like 1 hour 15 minutes, right? The academic hour.
Well, no, 50 minutes.
Oh, you have 50 minutes?
Really? Yeah. And then if you go for too.
Right, yeah. So the rule is like no differential equation. But we can use algebra. But the same way. So for instance, like you get to see in a different way. The amount of the material that they cover is really impressive. For instance, like special here was the full spin. Right. With all the problems and things like whatever. Paradox. Well, there is some kind of Gaussian back there. It's about typically like 40%.
Right. Okay, so we'll begin. All right, we'll begin the discussion session. If you have a question, please raise your hand and I will come and get you here and then there. And there.
Thank you. I have a small question on CP violation. Finally. And maybe another one on another subject. You said that CP was sometimes violated by a certain percentage, and it is also related to matter, antimatter universe. Can you calculate how much you need of CP violation to get this difference?
Yes, you can. And actually the answer I was going to save for the last lecture, because what is the answer makes me feel like Abel Tasman, as I said. He went out to find gold, and he didn't find gold. So I can tell you what is already now, what is giving away the clue of the last lecture. The CP violation represented by the CKM matrix is not completely enough to explain the baryon asymmetry in the universe. And it's not off by a factor of a few percent. It's not off by a factor of 10. It's off by a factor of, I think it's 10 to the 15, but it's maybe 10 to the 12, but it's a huge number. But that was going to save that for the last lecture, but okay.
Can I have one other question on the standard model? I guess these sort of particles in the fifth dimension that have a sort of general mass doesn't really, the story doesn't work for the normal particles because they have a fixed mass?
Exactly. So in other words, the way it works is like this. From the point of view of, as I said, from the point of view of a five-dimensional observer, this is just one five-dimensional particle with different possible fifth momenta. We see it as a tower of four-dimensional particles with different masses. Now, once we start doing model building, for instance, right? So the ordinary particles, as quarks, leptons, and so they have to be associated with the lowest lying excitation because they don't have fifth momentum, right? Obviously, they from that point of view, they are zero modes. And then your question is, what about their sisters and brothers from the, what about their corresponding towers, okay? And so we have a limit on the mass of the first excitation of the first sister of, for instance, of any standard model particle. It cannot be below around TeV. So there is a simply experimental bound on it. But other than that, yes, they can be around the corner. So in principle, for instance, there is a class of theories in which LHC, which predict that LHCs should also see excitations of, for instance, Kaluza-Klein partners of W and Z bosons and other states. In some theories, this situation is a bit more sophisticated, is that these particles, they are localized on this surface, like Alice in my example. And in that case, the mass gap between the zero mode and the first excitation may be very different from the particles which could move freely in extra dimensions. So there may be different mass gaps. Okay, so we'll discuss this, but that's the story. Yes. So for instance, one of the ways you could test theories of extra dimensions, precisely observing these sister excitations of ordinary states, and it's like it's pretty cool that we could see. So for us, they would appear as the tower of states. Some of them will be extremely weakly coupled, like graviton. So we will only see them through their collective effect. Some of them will be pretty strongly coupled, because they can carry charge and etc. And but there are clear predictions what should be their quantum numbers in each given model. Okay.
I have a question on the beyond standard model.
Okay.
So how we can deal with the particles with a spin in higher dimensions, more than 4, because we have a problem here.
Which problem are you referring to?
I mean fermions. How we can formulate a theory of in higher dimensions, I mean for fermions.
No, there is no problem. So, okay. So there is no... Let me go to the blackboard. So, no, a priori, there is no problem to formulate a theory of a fermion in any number of dimensions. So for instance, in 5, there is a well-defined representation of the 5-dimensional Lorentz group, fermionic representation. So there is no problem per se with having fermion in any number of dimensions. Now, there is a problem of so-called, maybe that's what you're referring to, of so-called chirality. And the reason is that, let's go to 5 dimensions. In 5 dimensions, there is no notion of chirality, okay? So in other words, sort of from the point of view of Lorentz group structure, certain dimensionalities, they have notion of chirality. You can define left and right. In certain dimensionalities, you cannot. Okay, that's a matter of fact. It's a matter of fact. So in other words, if I have 5-dimensional spinor, from the point of view of 4-dimensional observer, so for Bob, this is just a 5-dimensional spinor. He has no chirality. For Alice, this is a combination of 2 4-dimensional spinors, one with left and one with right chirality. Okay, so in other words, so this is, as a 4-dimensional observer, sees both chiralities. Now, the problem is how to isolate one chirality. For instance, if we want to construct a model, such a model like a standard model, which is chiral, okay? So for instance, right? And there are different techniques for it. So this is not this is a solved problem. So there are different ways. So in other words, what you have to do, somehow your compactification also has to spontaneously break high dimensional Lorentz invariance, so that somehow there is a distinction between left and right. And then you can have fermions which have different quantum numbers and they have different chiralities. So you can solve this problem. But it's true, right? If you have a 5-dimensional Minkowski space, there is no notion of chirality, which is very interesting actually.
Okay, and the second question, why we have the extra space dimension instead of one probably time dimension?
Very good. So yeah, so that's actually a very good question, because actually that question we could have asked already in within 4, right? Because we have 3 spaces and 1 time, right? Somehow spaces are more privileged. And so we can ask this question, I mean, can there be like extra time dimensions? And in fact, it's interesting that I would say that, for instance, in one of the greatest predictions of field theory could be that field theory predicts that there only should be 1 time. Why? Because you cannot formulate field theory, with gravity especially, reliably in any space with more than 1 time, because such theories do not make sense. What happens is that it turns out that if you try to formulate a theory in which you have time, okay? So for instance, like this, like Bob, imagine that Alice lives on, so this extra 5th dimension is a time, okay? So and Alice lives in 1 instant in that 5-dimensional time. Graviton that moves in, that can move in extra time, from the point of view of Alice, is seen as again as a tower, but not of the normal states, but of tachyons. You know, the tachyons are this state that seemingly they move faster than the speed of light. In reality, simply theory doesn't make any sense, because if you have a spin 2 tachyon, that's a complete disaster. Spin 2 tachyon also incorporates a component which actually has a negative norm. So you cannot even define a norm. So in other words, these theories make no sense. And to me, this is a great success of field theory, because field theory predicts 1 time, and that it's true so far, right? I mean, we have not seen the other one. But it's a very good question, yes.
Okay, and the last one, you mentioned the Higgs mass sensitivity to the scale.
Yeah.
It was the pole mass or what?
No, the mass, well, we can define mass as a pole in the propagator. So then we can renormalize this, so yeah, that quantity is sensitive. Of course, physical mass is that's end result. That is whatever it is, right? Okay.
Yes, I also have a question on the understanding model. Yes.
Okay.
If the gravitons actually do have resonances and have mass, won't that mean they self-interact?
No, absolutely, yes. So they self-interact, that's for sure. Gravity always self-interacts. The simplest way to see what would be the story with their self-interaction is that from the point of view of Bob. Bob sees simply 5-dimensional generalization of Einstein. That's it. So this is like 5-dimensional GR from Bob's point of view. From Alice's point of view, it's a 4-dimensional GR at large distances. And at short distances is something new, which, well, she sees as tower of states interacting in a very peculiar way. But of course, if she is smart enough, then she can reconstruct 5-dimensional GR, right? Okay.
My question is also for the
Okay.
model.
Sorry.
I have a question about how Lorentz boost will behave near the Planck length. It seems that 2 inertial observers can, through length contraction, observe different Planck lengths and therefore disagree on whether something should be a classical black hole or not.
Yeah, excellent. So the question, let me try to formulate this question if I understood it correctly. So what you're asking is that in special theory of relativity, I can simply go into the reference frame which moves I can arbitrarily boost the reference frame, and therefore I should see a length contraction in that reference frame. Now you're saying, suppose you have a box which has a normal, for you it's a normal length, and you are saying now that I boost myself, and I can boost myself arbitrarily, a priori there is no problem with it, and then I should see the Planck length of that box, okay? Now, this is not in any contradiction to what I said. Why? Because if you are boosting yourself in an empty space, then there is nothing special is happening. It's just a symmetry. If I'm the only one in an empty Minkowski space, I can boost myself as I like, and no problem. Now, to understand whether I'm still able to probe the boxes which are smaller than this Planck length, actually what I need is that not just you, but I need like infinite copies of you along the way with the infinite number of those boxes. Okay, then I can ask this question whether there is a paradox. But the point is that if there is infinite of you, then you are effectively making a background. And my boost relative to you is no longer a symmetry transformation. Then I'm literally moving along the background. And of course, once you're moving along the background, this is a physical process. So for instance, we can ask the similar question. We can take CMB, right? So we can ask the following question. Of course, if there was no CMB, we could take any particle and boost it with arbitrarily high velocity. With CMB, I cannot do it because eventually the interaction between the particle and the background will become Transplanckian, and then I'm back to this to the same story. Okay.
I also have a question to Björn Steinemüller.
Okay.
Could it not be possible that we already see these tower particles, for example, the electron, muon, and tau, which are exact copies of each other?
Right, fantastic. So yeah, so the question is, yeah, these will be very tempting, right, to identify electrons and muons and taus as essentially high-dimensional replicas of copies of each other. Now, I don't know any successful realization of this in the case when they are literally members of the tower, because their spacing is a little bit funny. It doesn't go like in. However, you can identify them as excitations of localized wave packets of this tower, localized in different places in extra dimension. That you can certainly do, yes. Yeah.
Thanks.
Raise your hand high so I can see you. Okay, we have one left here. Okay, we have.
Okay, then the second question. You mentioned before that you mentioned before that gravity is always attractive, or has to be always attractive.
Yes.
What's the reason for that again?
So, I mean, there is a consistency. So there are two reasons. First of all, of course, there's experimental one that we are here. But yeah, there is a consistency reason that the interaction between the localized sources mediated by any reasonable particle for which you can define a positive norm, either of spin 0 or spin 2, is always attractive. So if you have a repulsion mediated by spin 0, if somebody comes and tells you, oh, I have a theory of anti-gravity, here is my scalar and it's repulsive. This theory is inconsistent as a field theory. As something else, maybe it makes sense, but then I don't know. Why? Because in field theory, any such object would be a so-called ghost. We call them ghosts, because these are states for which you cannot define simultaneously a positive energy and a positive norm. So you have to sacrifice one of the two, and then of course it's a disaster because it's... So that's why. So interactions mediated by spin 1, of course, could be, as we know very well, they could be either positive or either repulsive or attractive. Okay.
Okay, there we go.
I have a question on raw data to physics. It could be two questions. The first one is a confirmation one. The raw data is saved generally, it is saved in hexadecimal format or it's in a binary format?
In what format? Magnetic?
Data, in what format it is saved?
Depends a little bit on the experiment. For example, now the LHC experiments basically are writing out some format which is provided by the root framework. So it's not ASCII files, it's some compactification, but it's based on some root formatting. Other experiments have used, well, in the past, other schemes which were maybe at some stage closer to an ASCII, or at least at some stage you could read it even by eye. But now it's some compactification is based on root packages.
And the second question is, we will be obtaining records twice, right? Once at the tier 0 level and once at the tier 1 level after it has been saved. So while we are analyzing this data, is there any consistent effort is done to check whether the records both the time appeared are the same or not? Like an efficiency checking for the record construction.
Yes, for sure there will be cross-checks, and when one has to make sure that the whole thing stays somehow coordinated and consistent, so that people analyzing the recos at the tier 0 should not get two different results from the people analyzing the data which come out from the tier 1. Otherwise, we have a problem. And there will be specialized groups or jobs which are responsible for, people responsible for doing this kind of validation and checking that after certain steps of reconstruction, you don't suddenly introduce big changes. You see improvement in resolutions, in efficiency, slight resolutions, but you should not see very big changes, because otherwise there could have been a problem introduced at some level. So this very generally we call validation, and where you look at standard distributions, where you know how they should more or less look like, and you check that they actually do look as they should.
The physicist has an access to this. When I do my analysis and I construct my own records and some data from there, do I have an access to those records that has been created earlier? Or?
Well, you should have, for the tier 0, the general idea is that the typical user analysis should not have access to the tier 0, because the basic idea is that this should be resources which are there for the experiment as a whole, with very centrally coordinated activities. There might be some user area for express type of analysis, but again, you have to define very well who can run there, with what priority. So the normal user should get access rather actually at the tier 2 level. Even at the tier 1 level, one probably will restrict it very much, because again, there are very important reconstruction jobs will run. And the idea is that the user analysis actually takes place on the tier 2s only, which is very much distributed. So we just have to make sure that the data distribution happens in an efficient and also in a fair way, that not certain tier 2s are privileged over others regarding certain data sets and so on.
Thank you.
Here, okay.
I have a question about beyond standard model. We know that using a particle in 5 dimensions, you explain the different masses of 4-dimensional particles, but we know that different particles may have different electric and maybe color. Can you explain electric and color in the same way using a 5-dimensional particle?
Oh, so the question is whether you can understand why 4-dimensional particles with different color or electric charge appear as a result of as a different states of a particle in some higher dimension, generalized higher dimension. Okay, that's the question, right? So it's not straightforward, for sure, for the why, because the electric charge, the reason why we get different masses in 4 dimensions, because mass corresponds to a momentum, which is a conjugate of the coordinate, right? So to get particles which have different charges as a result of some extra dimension, so that coordinate has to be conjugate to the charge, okay? Now, yes, you can introduce formally such a coordinate. At least immediately I don't see why you cannot. I don't see why, to which extent this will be any explanation for having these different particles of different charges immediately. Now, the better way, in some sense, sort of maybe accomplishes what you are asking for, is string theory. So in string theory, in some sense, these particles of different charge and the mass, and they appear as different states or different vibrations of the same fundamental entity, a string, which again, it lives in high dimensions. But for that, it's essential that it's more than a particle, that it's a string, that it has more, it has a richer harmonic structure of harmonics. But yes, otherwise it goes along the line that you are asking. So in other words, you can have a fundamental entity which lives in high dimensional space, which delivers all the variety of particles that we see around us.
Does that mean if you want to include more fundamental quantities, you have to introduce more dimensions?
No, not necessarily. So not necessarily. I mean, as I said, the string theory is an example that which sort of in the simplest incarnation, it lives in 10 dimensions. For instance, you can think of it as a string living in 10 dimensions. Now, the string, but because it's a string and not an elementary particle, on its own, it corresponds to an infinite tower of fields. Just in the same way, if you have a string of a violin, right? We have different harmonics, right? When you play the violin, you have different harmonics. So exactly in the same way, a fundamental string, it also has different harmonics. And these different harmonics, they correspond to different particles that we see around us. And these different harmonics, they have different masses and charges, and also other quantum numbers, okay? Right?
Okay, we'll need to leave it there. Let's thank our speakers again.